In this last part of chapter 6, we cover one of the most central results of linear algebra, namely least squares. When I first studied the subject of linear algebra, it was in a course given by Professor Kameshwar at UC Berkeley, who has a very inspiring and entertaining teaching style. So when he taught us least squares, he made the following quote that's written here, and that basically says it all. Least squares is undoubtedly one of the most important tools in science and engineering. Everyone should know least squares, even lawyers. So here is the least squares theorem. Let A be an m by n matrix with rank A equals to n and B be an m-dimensional vector. Consider the optimization problem where we want to find a vector x in Rn such that the 2 norm of the difference between ax and b is minimized. Then the least squares theorem states that this problem has a unique solution and the optimal vector x star in Rn is given by this explicit formula where we have in brackets a star a inverse times a star times b. Note that this special expression here is an n by m matrix, which is often called the pseudo-inverse or the Moore-Penrose inverse of A. For the proof of Theorem 614, first observe that the matrix A star A is an n by n matrix which is invertible by lemma 6.13, and that's because the rank of A star A is equal to the rank of A is equal to n by Theorem 6.11e. Since the matrix A star A is invertible, our solution candidate from the theorem, which we call here x naught, is well defined, and we can define P and Q as follows. We expand the difference of ax and b by subtracting and adding the term ax naught, and then we define the first 2 terms as the vector p and the second 2 terms as the vector q, so that ax minus b can be written as the sum of p and q. Observe that q equals to the error vector ax naught minus b, whose norm we claim is minimized by the candidate solution x naught, and p is the difference in the error vectors of any vector x, namely ax minus b, and of the candidate solution x naught, so ax naught minus b. A short calculation reveals that p is orthogonal to q, so we form the inner product of the vectors p and q, which in the case of Cn is given by p star q, where we can substitute the definitions of p and q, which yields x minus x naught in brackets star a star times in brackets ax naught minus b, where we can now pull the a star into the second bracket and substitute our expression for x naught, which yields this result in the square brackets, where we observe that at the beginning of the first term we have a star a multiplied with a star a inverse, so this of course equals to identity, and then we see that we have a star b minus a star b, so the whole thing equals to 0. By using the Pythagorean theorem, it follows that the squared norm of ax minus b, which is equal to the squared norm of p plus q, and since p and q are orthogonal, this is equal to the squared norm of p plus the squared norm of q, which clearly is always greater than or equal to the squared norm of q. So since q equals to ax naught minus b, this implies that x naught must be the optimal vector of the least squares problem. To show the uniqueness of the optimal vector x naught, suppose there exists another solution that we call x bar, which produces the same norm of the error vector. So the norm of ax bar minus b equals to the norm of ax naught minus b. Following the argument above, we have the following equation, namely the norm of ax bar minus b squared equals to the norm of a times in brackets x bar minus x naught squared plus the norm of ax naught minus b squared. Now, since these two terms are equal by the optimality assumption, we must have that this term here equals to 0, and hence the vector a times in brackets x bar minus x naught must be 0, which implies that the vector x bar minus x naught must be 0 because the null space of A equals to the 0 vector due to lemma 613 by using the fact that the rank of A equals to n, and hence the range space of A equals to Cn. Now what we have here is stating exactly that x bar equals to x naught, so we have proved uniqueness and we have finished our proof of the least squares theorem.